let us go ahead into chapter 7. Sequences and series of functions. Okay, and so this is the last chapter that we'll do. And the reason I include this is because I think there are a lot of, in the Claremont system, I think there are a lot of people who take 131 and not 132, which I think is a mistake. But that it's almost geared, the system is almost geared to allow people to do that. To me, it's sort of like building the bottom half of a house. You build the walls, but you don't build the roof, which is clearly a mistake. But since there are people who do this, I think I'd like to include one of the most important topics of that second section, which is the notion of uniform convergence. Okay. So, for example, when I teach the Fourier analysis course, the notion of uniform convergence is pretty crucial. Okay. So here we go. Suppose you have a subset of a metric space, so X a metric space, and you have a bunch of functions on that subset. Okay, so you have a sequence of functions, f sub n, right? N equals 1, 2, 3. Right? You have a sequence of functions. They all map into the complex numbers. So complex. You have a sequence of complex valued functions. Okay, and you have that the limit. So if for each point in E, the limit of s sub n x as n goes to infinity exists, call it f of x, then we say the sequence f sub n converges pointwise to f. Converges pointwise to f. Okay. So you take each point in your domain and you take the limit of the values at that point. That converges to some value. You call it f of x, right? And that defines a new function. Okay, and we say that the sequence converges pointwise to that function. Okay.
And that has to be for every x.
For every x in, so converges pointwise to f on E. Okay. So let me give you an example. If you're looking at, for example, a function on 0, 1, where fn x is x to the n, okay, so we have a function on the interval 0, 1, right? We choose a point x, right? We choose a point here, and then we look at the limit of fn x as n goes to infinity, right? The limit of x to the n as n goes to infinity. Okay, well, what is that going to be? As n goes to infinity, I've got this point here. Suppose I choose a point smaller than 1. It's going to become, you are whispering it? 0. Yes, 0, right? Because you start off with some number that's smaller than 1. You take powers of it, right? And it's going to decrease down to 0. Right? If I'm at 1, then what happens? Then it just stays at 1, right? Okay, right? So what we have is that this sequence f sub n converges to the function f of x being 1 if x is equal to 1 and 0 0 otherwise. Right? So this is a point, what's called pointwise convergence. Okay, right, in the picture, right, your first function is just the x, f, f of x equals x. Your second function is the square function, then the cube, then take the fourth power, fifth power, and so on and so forth, right? Right, and becomes flatter and flatter as time goes on. As n goes on, function becomes flatter and flatter and flatter, right? And in the limit, right, every point is going to converge to 0 except for 1, which stays at 1. Right? So this converges to this function, right? This is f, right? F1, F2, etc., etc. Yeah, you have a question? No. Okay. Another example. F sub n x is, again, let's say from R to R. F n x is defined as the characteristic function of, say, n plus 1. Are you familiar with this notation, characteristic function? Okay, what it means is that it's going to be 1 if x lies in this set, this interval, n plus 1, and it's 0 otherwise. Okay, it's what's called the indicator function or the characteristic function. Use the Greek chi for the characteristic function. Okay, it says if your point is in the set, you give you a 1. If your point's not in the set, you give it 0. Okay. Okay. Right. And what happens? What does this function converge to pointwise? How does this function? How do this sequence of functions converge? Well, you take any point. Let's say you take some point here, x. Okay. Then, right, at some point, let's say that this is 0. You've taken a positive point, right? So for the most part, this function, the function at x is going to be 0, right? But at some point, the function's going to cross. You're going to land in the interval of the function. At that point, that time you'll be 1, and then afterwards you'll be 0 again. Okay. So at every point, for the most of your life, you're nothing, and then at one point, glorious point in your life, you're something, and then after that, you're back to nothing again. I didn't know what this says about that. Okay, so you converge to 0, right? Right. Ultimately, everybody becomes 0. Maybe this is just like human existence, right? You're alive, right? For most of history, you're nothing. At some point, you're alive, and then after that, you're dead again. Okay. Okay, I don't know what you want to think. In any case, converges pointwise to 0. So this converges to the to the function. So converges pointwise to this, to the 0 function. Okay. Another example, fnx is, say, n times the characteristic function of the open interval 0, 1 over n, comma x. Okay. So, right. So these guys, if you're looking at the graph, right, the time 1 is between 1 and 2, it takes the value 1, right? At time 2, the second function, so this is f1, f2's graph takes on the value 1 between 2 and 3, and so on and so forth, right? So it's this thing that's just moving across, right? Like that. And it goes off to its infinity. Okay? Okay. What about this function? What does it converge to? Well, this is the indicator function of 0, 1 over n, the open interval 0, 1 over n. Right? So at 0, it's actually 0. Right? Because 0 is not in this set.
Oh, I see.
Right?
Okay.
0 is not in the open interval. So at 0, it's always 0.
So converge to 0?
Converge to 0, exactly. Right? Because you see this guy, right? The first guy, time 1, takes on the value 1 on the interval 0, 1. The second guy takes the value 2 on the interval 1, 0, 1 half, then the value 3 on 0, 1 third, then this value 4 on 0, 1 fourth, and so on and so forth, right? No matter what point you choose, right? No matter what point you choose, well, it will be 1 for a time. It will be 1 for a time, but then eventually, it'll be 1, and then, depending on where you are, it'll be 1, 2, 3, well, but then it will become 0, right? Once 1 over n passes you, then you become 0 again. Then you become 0, right? Okay. Yes?
Sorry, could you repeat the last part one more time?
Yeah. So no matter what point you choose, so here's the interval 0, 1. 0, 1. So I choose some point near x, right? And the thing is that at some point, as n gets large, this 1 over n is going to get smaller than x, right? And past that time, the characteristic function is not going to see you. You're not going to be in the interval 0, 1 over n, right? So maybe for the first few, right, for number one, in this picture, for number 1, number 2, number 3, and number 4, and maybe number 5, I have positive values, and the values will be 1 and 2, and then 3, and then 4, and then 5, right? But then once the 1 over n crosses past my x, then I become 0, right? Because I'm not going to be in the interval 1 over n, 0, 1 over n forevermore. So again, this function also converges to the 0 function. Converges pointwise. Okay. Okay. Here is a non-example. Which was described to Winona.
So for that example,
Yes.
what if it's a closed interval?
If it's a closed interval, then at 0, it's going to tend towards infinity, right? But then at every other point, it's going to go to 0.
Okay.
Yeah. Okay. Okay, everyone all right? Okay, next example, the Blimp functions. So you take the interval 0, 1. These guys only take value, the domain is 0, 1. Okay, and the first Blimp looks like this. First Blimp function looks like this. So at the height of 1, it's just the whole, takes on the value 1 throughout. Okay. Then, so that's f1, the graph of f1. f2, it's going to look like this, just at the half of the interval. Okay. F3 is going to look like this, 0, 1. So you take that first half, and you start from the end of this guy, and you go 1/3 forward. Okay. You go 1/3. So from 1/2 to 1/2 plus a third. Okay. The fourth guy, you start from the end of that guy, and you go 1/4 forward. Okay. And you keep on adding, decreasing. You keep on adding one. The length gets shorter, like 1 over n. Okay. Right. The length here is 1. The length here is 1/2. The length here is 1/3. 1/4, and so on and so forth. Okay, and you keep on adding to the end, and you use a wraparound. Okay, so if you go past 1 over here, then you wrap it around and make it come around here. Okay, so it's just like playing an old asteroids game.
So that's why F2 starts at 0.
Yeah, that's why F2 starts at 0, because I wrapped around from 1 here. Yeah.
So the last one is start from 1/2 plus 1/3 plus 1/4.
It starts from 1/2 plus 1/3 and goes to 1/2 plus 1/3 plus 1/4. Yeah, Alex.
So would it be, since the summation of 1 over n is divergent, it means it's just going to wrap around forever?
That's right.
So-
That's right. So it'll keep on going. Very good. It'll keep on going. So that means that no matter where you are, you're going to see the blimp. So this is a blimp, and it's shrinking in size. Okay. No matter where you are, you're going to see the blimp infinitely many times, right? Because summation 1 over n doesn't converge, right? It's infinite, right? So the sum of the lengths of these guys is infinite. So you're going to just keep on seeing the blimp over and over, even if it gets smaller. The time the time it takes you to see it is going to take longer and longer, but you're going to see it infinitely many times no matter where you are. Okay, and so even though the blimp is getting tiny, right? The blimp is getting tiny. You're still going to see it infinitely many times. Okay. So this function, this sequence of functions converges to. It doesn't converge, right? It doesn't converge because the values are going to be, it's going to be something like 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, and then 0. Even you have a longer space of time of waiting, but then you see it again. You wait even longer, and then you see it again, and so on and so forth. So it's going to be a sequence of zeros and ones, even though the ones are farther and farther spaced out. Okay. So no matter where you are, none of these guys will converge. Okay. Okay. This is actually a different sort of, people like to describe this as convergence, what's called convergence in measure. Convergence in measure. It's not pointwise convergence, but you sort of think that this function, the functions that you get later on are for the most part 0, right? They just they're 1 on a very, very, very tiny part. Right? It's pretty much the 0 function, right? So this is actually something that you'll see in a real analysis course called convergence in measure. This sequence converges in measure to the 0 function, although it doesn't converge pointwise to the 0 function.
So if it's not 1, it is 0?
Yeah. Yeah. So this is the graph here is it's 1 here, it's 0 here. It's 1 here, it's 0 here. That's it. Yeah, me.
So pointwise it diverges?
Pointwise it diverges, yeah. Does not converge. Okay. Another example. Fmx is defined as 1 if m factorial x is an integer and 0 otherwise. In other words, i.e., if x is p over m for some integer p, p over m factorial for some integer p. What do you think about this function? Well, suppose you have an irrational number. You have an irrational number. You multiply that number by factorials. Do you ever get into the integers? No. Right? So you're always 0. Right? So this function in the limit, right, if x is not rational, then f of m is 0 always. Right? And so it's 0. Okay. Now, what if x is in the rationals? Well then, it'll be 1, right? Because at some point, x is going to be p over q for some pair, right? At some point, you're gonna get at least past q at the qth fq, of course, is going to be 1 because p over q times q factorial is in the integers, right? And certainly everything past that point will be 1. So you know that at least at this point, there's some point where you turn into 1 and you stay 1 up. You stay 1 forevermore. Okay. So this, in that case, the limit of these guys is 1. Right. Okay. So this turns into the limit of these guys. The pointwise limit of these guys is the indicator function for the rational numbers. Right? It'll give you 1 if you're rational. It'll give you 0 otherwise. Right? If you're irrational, 0. If you're rational, then 1.
Do you need the factorial though? Would it just be m(x)?
Well,
Because eventually m will equal q.
but then
But then when you go past it,
when you go past it, you're in trouble. Yeah. Exactly. Good. Okay. So let's see. The last. So maybe I'll stop there with the examples, and I'll start talking about why we're using these examples. Let's make some observations. So observe. If the Fn are all continuous, must F and converge pointwise. So say you have some sequence that converges pointwise to some function f. And suppose they're all continuous. If they're all continuous, does f have to be continuous? Does that imply f is continuous? No, right? What example? You can probably guess. It's the first example that we showed, right? The x to the n one. All those guys, x to the n, so no. X to the n is continuous, right? These guys were all continuous on 0, 1, but the limit was 0 everywhere except for 1. It was 1 at the end point, right? So the limit was discontinuous, right? What about differentiability? Suppose your function is, you have a bunch of differentiable functions. Does the limit have to be differentiable? The pointwise limit, does it have to be differentiable? No. No. For example, you can have things that ultimately turn into the, the absolute value function. Right? But start off, you can have some functions that go like this, but then become spikier and spikier, and then ultimately converge pointwise to the absolute value function. Right? Or this is sort of an example of that, right? Because these guys are all differentiable, but the limit is discontinuous. So Fn all differentiable. Does it imply f is differentiable? No. Even worse, you can have, in fact, limit, pointwise limit, and differentiation don't commute. Okay, so here's the example from the book. I mean, these are all from the book. Here's the example. You have this sequence, and suppose you take the limit of this sequence. What's the pointwise limit of this sequence at any point, any fixed point? Got this 1 over n as n goes to infinity. I mean, the sign is becoming the period is becoming shorter, but still, the values are bounded between -1 and 1, and so when you divide by this, the values are going to decrease to 0, right? So the limit of this is 0. It's the 0 function, right? At every point, you're going to get the 0 function, right? So I take the limit first, and then I differentiate, right? So first take the limit, I get the 0 function. If I differentiate, then I get the 0 function, right? So the derivative of the pointwise limit is the 0 function. Okay. But if I differentiate, you see that I get square root of n cosine nx. Right? And when I take, so if I differentiate first, I get this, and then I take the limit, what do I get? Well, I get something that doesn't converge, right? It goes to infinity, or I mean, it doesn't converge in fact. Okay. This goes to infinity, but this goes back and forth. Okay. So what you see is that even if my functions are differentiable and the pointwise limit is differentiable, still doesn't happen that the limit of the derivative equals the derivative of the limit. Okay, so it doesn't commute. Right? Can't change the order. Okay. Okay. We haven't talked about integration, but that function, so pointwise limit and integration. Pointwise limit and integrability. Okay, those functions that we introduced earlier, fmx being 1 if m factorial x was an integer and 0 otherwise. These guys are all integrable functions, are all Riemann integrable. Right? You just take 1 over m factorial. I mean, what is the function? What's the graph look like? It looks like this. It's 1 at 0. It's 1 at 1 over m factorial. It's 1 at 2 over m factorial, and so on and so forth. Right? And it's 0 everywhere else. Right? So it's a function that, for the most part, is 0. Right? It takes on the value 1 only at these discrete points. Right? This is an integrable function. Right? The integral, the Riemann integral of this guy is 0. Right? Okay. But if you take the limit is the indicator function for the rational numbers. Okay, what does that look like? it's 1 at every rational number and 0 at every irrational number. Right? If you graphed it, no matter how thin your ink was, it would look like you had a solid line up here and a solid line down here. Right? At every rational number, it takes the value 1. At every irrational number, it takes the value 0. Right? And if you remember your calculus 2 or calculus 1, when they talked about how you define an integral, right? Maybe I don't remember how you. I don't know how you guys did it. You either did it with upper sums and lower sums, or you did it with Riemann sums, where you choice of point didn't affect the Riemann integral. In any case, however finely you partition your base, you know, you could either choose 1 as your sample point, choose a rational point as your sample point, or an irrational point as your sample point, right? And so it's not really clear what your value is going to be. You're either going to your value, the integral of 0 to 1. What is it? Is it 1? Is it 0? Is it some number in between? With the Riemann integral, you can't tell. There's no way to define it using the Riemann integral. There is a way to define it using something called the Lebesgue integral. And for that, you have to stick with math a little bit longer and take 137.
Oh, wow.
Okay. Same thing with the Blimps. The Blimps, 137. Convergence with respect to measure.
Can you explain why you need the m factorial again?
Because suppose I'm looking at the number 1 over 100. Okay. At time 100, I would get a 1. Right? If I don't have the factorial, and so I think what you're asking is, could I do it like this? Is that what you're doing? Is that what you're asking? Yeah. So if I had it like this, and I'm looking at this point, x is 1 over 100, right? Then at time 100, I would get a 1, but then at time 101, what would happen?
No.
I would not be in the integers, right? And so this thing would just be flipping back and forth, right? But if I've got m factorial, well, then at time 100, I multiply by 1 over 100, I get 100 factorial. And then after that, there's always a 100. There's always a 100, right? Because at time 101, I have 101 factorial, which is 101 times 100 times 99, et cetera, et cetera. So if I have the factorial in, then this thing really does converge to 1 at rational points, but otherwise, no. It's going to be flipping back and forth. Right? Without the factorial, then after 100, when am I gonna get a 1? Well, at 200, 300, 400. Right? So every 100 turns, I'll become 1, but then 99% of the time, I'll be 0. Right? And it doesn't converge. Yeah.
Is factorial only defined for the natural numbers?
Yes, but it can be generalized using something called the gamma function. Which you would see if you continued to the next course in 132. Okay. Yeah. Okay. So what do we see here? You have a bunch of Riemann. You have a bunch of integrable functions, and they converge to something, and that thing is not integrable anymore. Okay, so differentiable functions converge to something that's not differentiable. Integrable functions converge to something that's not integrable. Okay, so pointwise convergence doesn't preserve nice properties. It's sort of immoral. Pointwise convergence, even if your functions have good properties, if they converge to something, that thing that they converge to might not have the properties that you wanted. Okay, and that's the trouble. Okay, so let me, along the lines of what I did with differentiation, let me say that limit and integration also do not converge. Integration also do not converge. for example, if we have that guy f sub n is n times the characteristic function of 0, 1 over n, then you see that the integral of each of these guys is 1, right? Because the width of the base is 1 over n, and the height is n, right? So the amount of stuff that's there is volume 1, area 1, right? So whenever you integrate it, you get a value of 1, right? So if you take the integrals of these guys and you take the limits, you get 1, right? But if you take the integral of the limit of the pointwise limit, well, as we said before, the pointwise limit is the 0 function, so you get 0. Right. These guys are getting taller. These guys are getting taller, but they converge to the 0 function pointwise, and the limit of the integrals is not the integral of the limit, so you don't have commutation. Another relevant example that you'll probably see again when you talk about Lebesgue integration is this one, the other one. Right, same thing, right? The integral of each of these guys is 1, right? But again, if you take the limit, integral of the limit, you get 0. Right? And so you see that there are two different kinds of problems that can occur. One is that your meat, the meat of your function, it races off towards infinity, right? So the domain, just heads off to infinity, and here you have trouble where it heads off towards infinity in another way. You will see in real analysis, you'll see theorems which tell you when it is okay under what conditions you can change the order of limit and integration, and it won't change the value. These are called dominated convergence theorems. A lot of real analysis is doing these sort of convergence theorems. Okay, so just one last definition before we start. Definition and example before we start doing some actual work here. So if an infinite series converges for all x in the set, then we can, it's just talking about convergence of a series, right? Suppose at every point, this infinite series converges, right? So at each point, you have an infinite series. Suppose that thing converges. Then you've got a function, right? Then we say that this infinite series converges to f. example. On the real numbers, let f sub n be defined as x squared over 1 plus x squared to the n for n equals 0, 1, 2, etc. Okay. And then let's consider the sum of these guys. Okay. So the first thing to notice is that at x equals 0, well, everything that you're summing is 0, right? So it's just 0. This infinite sum will be 0. Converges to 0. Okay. If x is not 0, for x not equal to 0, well, let's pull the x squared out. We get 1 over 1 plus x squared to the n, summation from 0 to infinity. Okay. Now that's a geometric series, right? You're taking this thing to the nth power. Right? So that's going to be 1 over 1 minus 1 over 1 plus x squared. Okay. Remember, for the geometric series, it will converge to 1 over 1 minus the ratio of successive terms. Summation r to the n converges, if it does, if r is smaller than 1 in magnitude, to 1 over 1 minus n. Right? So you get 1 over 1 minus the ratio of successive terms. Right? You do a little bit of elementary algebra, and you get 1 plus x squared. So this would be, this series converges pointwise to this function, right? The function that's 0, 0 at 0, and 1 plus x squared everywhere else. This is the thing it converges to. As an example, another example of the bad interaction between continuity and pointwise convergence. These guys are all these guys are all continuous, but even a sum of continuous functions need not converge to something continuous. Okay. So what you should get out of all of this is that convergence is bad, right? That it doesn't preserve what you would like it to. Or convergence is sort of destructive. Okay. But all hope is not lost. We have a different kind of convergence that works. So, and that kind of convergence is called uniform convergence. So let's go back first. Okay. If we say f is the pointwise limit of the f sub n on E, and we want to express this in our epsilon language, right? What is it? How do we say it? Well, at every point, this limit converges to this, right? At every point, right? At every x in E, the limit of f sub n at x is f of x. Right? But now let's state it in the epsilon language. at each point for each x and e, given epsilon greater than 0, there exists an n such that n bigger than n implies that fn x minus f of x is smaller than epsilon. Right? That's just a direct translation. Right? You converge at every point. At each point, you converge. Okay. What will I give as the definition of uniform convergence? You have a bunch of functions on E, and you have some other function on E. We say the Fn converged uniformly to F on E if, what am I going to say?
You want the same n for each x.
That's right. You want an n that works for all x. Right? So if given any epsilon, there exists an n such that for all get n bigger than n, and for all x and e, fn x minus f of x is smaller than epsilon. Okay, so what's the picture that you want to have? What does this mean pictorially? Here, what we have is this sort of situation, right? We have a bunch of functions, and if you fix any point x, right? Then, and you look at this sequence of points, right? Then you can make them arbitrarily. You can find an n so that past that point in time, they're all all the functions at that point are within epsilon of the limit value. Right. So that is, we define. You take an epsilon, and you know that there's some n past which all the values are inside that neighborhood of the limit value. Okay, right? And over here, right, if I take a different x, I take epsilon, I have to choose a different n. Right? The n that worked here may not be the n that works over here. Okay? Okay. Now, what does uniform continuity mean? It means that there's some function f, and so here's my domain E. It means that if I take an epsilon, a tube of radius epsilon around here, then at some point in time, all the graphs are going to be inside the tube. Okay, right? So it'll be something like this. These guys I have like this, right? But then at some point, I cross into the tube, and I don't, right? I cross into the tube. So there's some n, so that for all points in epsilon, all values are within epsilon of the limit value, right? So it has to happen simultaneously, and it has to happen uniformly. Okay. So there's a tube here, no tube over there. Okay. Pointwise convergence, uniform convergence. So right here, this n depends on x and epsilon. And here, this n depends only on epsilon and not on x. Okay. Along the same lines, we define a series converging uniformly. I'm not going to write it up. It just means that the sequence of partial sums converges uniformly to the limit. So if the sequence of partial sums converges uniformly in the above sense. Okay, everyone all right? Alex?
I guess. Would that function uniformly converge?
No, actually.
No.
Yeah, it won't. And you'll see why. Well, it's easy to see why. Right? Take your tube. Okay, take your tube. Can you find an n so that all the x to the n all their graphs live inside the tube?
No, because that's to go up.
At some point at the end, it's going to exit the tube. So no. Good. Doesn't converge, you know. Okay. There's a simple way. There's a way of looking at uniform convergence called the Cauchy criterion for uniform convergence. So suppose we have a sequence of functions. So question? Question? No?
You're just saying Cauchy does everything.
Cauchy does everything. Yeah, I'm afraid so. Yeah. Yeah, amazing. Okay. So you have some sequence of functions that converges uniformly on E. If and only if, for all epsilon greater than 0, it exists in M, such that if M and N are bigger than or equal to N, then what am I going to write? I should have just told you to write down the theorem. My goal in each class is to get to a point where I don't have to do anything. I just say, so what's the next theorem? How do you prove it?
Assuming the distance of f of n, comma, f of n is less than epsilon.
Yeah. Yeah, exactly.
Oh, we can use that distance to do things that it's complex.
Yeah, complex numbers, yeah. Okay, take a minute and see if you can prove it. Do this way first, and then try the other way. try to see that, or just, even if you don't write it down, try to see why that's sort of intuitively obvious. Okay, who would like to say something about the forwards direction? You're trying to see that there's some time, so you fix your epsilon, and you're trying to see that, so you know that these guys satisfy the tube condition. Given any tube, there's a time past which their graphs lie inside the tube. And you're trying to show that given any epsilon, there is some time past which all values are smaller than, the distance between pairs of values is smaller than epsilon.
Choose epsilon that guarantees if n greater than n, then the distance will be less than epsilon over 2.
Yeah.
And then use the triangle inequality.
Yeah, exactly. Right? So just choose a tube of width epsilon over 2. Right? So since they converge uniformly, Fn converges uniformly. So there exists some n such that anybody bigger than that implies that your distance from the function is smaller than epsilon over 2. Right? So here's your limit function. You take the tube, the epsilon over 2 tube. Right? Take epsilon over 2 tube. Then, if you take, you know that all the functions lie inside there, right? So at any point, right, the two values lie inside there, and so their distance must be smaller than epsilon. And then, if n and m are bigger than n, we see that the distance from fnx to fmx is smaller than or equal to the sum of the distance from this guy to f plus the sum of the distance from f to the other guy, right, which is smaller than epsilon. Okay. Now, in the opposite direction, it's basically the same sort of argument. You say, well, look, suppose that we have, suppose for epsilon greater than 0, there's an n such that n bigger than n and m bigger than n implies that fnx minus fmx is smaller than epsilon. That implies that for each x, fnx is Cauchy. And so converges to some f of x, some value. Okay. So at least we have pointwise convergence to start off with, right? So this is basically to say we have pointwise convergence. Okay. Okay. But now we want to show uniform convergence. So given epsilon, choose n such that n and m bigger than n implies fnx minus fmx is smaller than epsilon over 2. And then take the limit of one of them. So let m go to infinity, and we get fnx minus f of x is smaller than epsilon. What we really get is less than or equal to epsilon over 2, which is smaller than epsilon.
How does that imply, like the third line, that fn of x is Cauchy? Yeah.
This is, so this is what we start off with, right? Given any epsilon, there's an n such that if m and n are bigger than n, then the distance between these two guys is less than epsilon, right? Just think this is exactly how we define a Cauchy sequence, right? If you have some sequence a sub n, when do we call it Cauchy? We call it Cauchy if there's some time past which a sub n minus a sub m is smaller than epsilon, right? Right. So that's exactly, you're just getting confused because I have a function here rather than row sequences. Okay. You have a sequence. This is it. So you can think of an as the sequence fnx. That sequence is Cauchy. I think you might be getting confused between the sequence of functions and the sequence of values of the function at a point. This is the sequence of values of the function at a point. Values of the functions at a point. Yeah, so what we're doing now is not looking at sequences of points, but sequences of functions. Okay. Our functions are now our points. Okay. And the ultimate theorem that we're going to get to is one which is sort of like the Bolzano-Weierstrass theorem, where you say you have an infinite number of points, and you're in a compact set. Then you're guaranteed a convergent subsequence. Okay, so that's basically what we're going to be going for. You have some sort of sequence of functions. When are you guaranteed a uniformly convergent subsequence? Okay, so it'll be like it's an analogy to the previous result, the previous compactness result, right? You've got a compact set, you've got an infinite number of points. You're guaranteed that there's going to be a convergent subsequence. Here, same thing. We're going to have some sort of compact set of functions. Okay, so, and what that will be, it won't be. We'll have to clarify. Have some sort of compact set, functions that exist in a compact space, and then under certain conditions, you'll get a convergent subsequence, a uniformly convergent subsequence. Yeah, that's basically the main goal of this section, the theorem of Ascoli-Arzela. Okay, so here we have uniform convergence, stated in the Cauchy way, right? So. Maybe make this happens for all x. Okay. Right, and if you're talking about a series, then you have the same sort of thing, right? If you have a series, how is this condition going to change for you? Yeah.
Does this result hold for just like generalized metric spaces, or does it have to be complete metric space?
It has to be complete, right? Because we have a Cauchy sequence there, right? You're talking about a function in. What you're talking about this part here,
Yeah.
right? Yeah. It has to be complete, because otherwise, what do you convert it to? Yeah. Okay. Back here, if we're talking about a series, then we're going to replace this condition with the size of the tail condition, right? You know, that you need to have this thing. This thing needs to be smaller than epsilon, right? So you just change it in the way that you know. Okay, and that leads us to the following simple but very useful convergence test called the Weierstrass M-test. So again, you have a bunch of functions, and so it's this. If the functions are all bounded by constants, so each function has a bound. F sub n is bounded by some constant m sub n. And if you know that the m sub n converge, then the sum uniformly converges. Simple theorem, but it's pretty handy. It shows up in, if you take a course in complex analysis, then you'll see this, maybe. I hope you would see it. You should see it. It's a crime if you didn't see it. Did you guys see it? I hope so. Yes, you did. I just choose to believe that you did see it. Those of you who have taken complex analysis before. Okay. So, so the proof, right? We're trying to show that this thing uniformly converges, right? So, by the Cauchy criterion, try to prove it in 1 minute. Okay, I'll give you 1 minute to prove it, and then, and if you can't, then I'll show you. But I think you might be able to get it. By Cauchy criterion, you want to show that you can make the tail smaller than, given any epsilon. There's this an n such that, you want to show that given any epsilon, there's this an n such that if n and m are bigger than n, then the size of the tail is smaller than epsilon. Right? What do you need to say? Just 2 words?
Triangle.
Triangle inequality, yes. Triangle inequality. By triangle inequality, someday I'm going to change that, and it'll be 2 different words. You all feel embarrassed. By the triangle inequality, right, we know that this thing smaller than this thing, right? Which is smaller than this. Oops, those should be k's. There should be a k here. Right? But we already know that this thing converges. Right? We already know that this thing converges, so by the Cauchy criterion for convergence of series, we know that there exists an n such that if n and m are bigger than n, then this thing is smaller than epsilon. The end. Right? Since this thing converges, there exists an n such that n and m bigger than n implies that this thing is smaller than epsilon, right? Use that n.
Could you just be done after the triangle inequality line?
If you understand what you're doing, yeah. I mean, this is sort of spelling it out.
Okay.
Yeah. But no, otherwise no. Let me just take 1 second for completeness to write down a very simple recharacterization of uniform convergence. Yeah. Which I'll leave as an exercise. I was going to make you do it as an exercise anyway. So, suppose that pointwise, you have pointwise convergence, and you let m sub n be defined as the supremum of the difference between m sub n, so f sub n and f over the whole set. Then f sub n converges uniformly if and only if the limit of the m sub n is 0 as n goes to infinity. This is a funny notation. I never saw it when I was younger, but at some point I saw this double arrow means converges uniformly. I don't know if you like it. So I'll leave that to you as an exercise. But it's actually very, very trivial. It's almost a tautology. Okay, that's it for today.